Okay, this is chapter 4.6, Similarity and Transformations. So the essential question, when a figure is translated, reflected, rotated, or dilated in the plane, the image is always similar, or is the image always similar to the original figure? So two figures are similar figures when they have the same shape, but not necessarily the same size. What you will learn in this chapter is how to perform similarity transformations, describe similarity transformations, and prove that figures are similar. So here are two triangles that are similar. Same shape, different size, different location, similar. Okay, so before we get into the examples, performing similarity transformations, I just wanted to read this to you. A dilation is a transformation that preserves shape, but not size. Okay, so a dilation is not a rigid motion. A similarity transformation is a dilation or a composition of rigid motions and dilations. Two geometric figures are similar figures if and only if there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape, but not necessarily the same size. Congruence transformations preserve length and angle measure. Okay, let me repeat that. Similar figures have the same shape, but not necessarily the same size. Congruence transformations preserve length and angle measure. When a scale factor of the dilations is not equal to 1 or -1, similarity transformations preserve angle measure only, not side length. Okay. Okay, so finally we're on example 1. Here we go, performing a similarity transformation. So it says to graph triangle ABC with these vertices. So let's do that before I read any further. Graph the triangle. A, -4, 1. Here's A. B is -2, 2. And C is -2, 1. Okay, so there is the triangle. Here is A. Here is B. Here is C. Let me get my straight line command, make it red. And that will be from here to here, here down to here, and then finally here to here. Okay, so let me just fix this. I kind of dragged it so it's not perpendicular. All right, so there we go. There is triangle A, B, C. I'm just going to make this one piece. Okay, so there is triangle ABC. So I've graphed that. And its image after the similarity transformation. So there's going to be two transformations. So we're going to take this triangle ABC and we're going to translate it. And let's do a different color for that. I'll do green for this one. So this is going to be the prime translation right here. And we're going to take X, Y, and we're going to, this is called a rule. Our rule is to take X to X plus 5 and Y to Y plus 1, which just simply means move to the right 5 and up 1. Okay, so I'm just going to do a copy just to save time. So I have this triangle right here I made a duplicate of. So if I shift this to the right 5, 1, 2, 3, 4, 5, and up 1, it would end up right here. So I'll change that to green, and I'll put prime values on the A, B, and C. Okay, so there it is, and let me make that all 1. All right, so there is our image after our pre-image has moved these values. Now, in order to show your work, what you really should do is take the vertices and say A, which is -4, 1, is going to go to -4 plus 5, 1 plus 1, and give me a prime, which is -4 plus 5, which is 1. Okay. And a 1 plus 1, 2. So my A prime is over 1 up 2, and sure enough, that's where my A prime is. And then do B. B is negative 2, 2. I'm going to perform the rule, which is add 5 to the x, and take the y and add 1. That is going to give me b prime, which is negative 2 plus 5, or 3. 5 plus 1, 6. Go over 3. Is that right? 6? No, 2 plus 1 isn't 6. 2 plus 1 is 3. So over 3, up 3. 2 plus 1 is 3. Over 3, up 3. There's b prime. And then finally, c is at the point negative 2, 1. Performing this rule, you take your x plus 5. You take your y plus 1. You get your c prime, which is negative 2 plus 5, 1 plus 1. So over 3, up 2, and that is where c prime is. Okay, so that's how you do it manually. And plot the points, draw the lines. I cheated and copied it over and carried it up there, and same thing. So now we're going to dilate this, okay, about the origin. So whenever it doesn't say what you're dilating around, your point of dilation is going to be the origin 0, 0. And it says to dilate this by 2x, 2y. All right, so that is our k. K, our scale factor, equals 2. Because I have a 2 here and a 2 here, we're just going to multiply all these. So I'm going to take my a prime, which is 1, 2. I'm going to take my b prime, which is at 3, 3. And I'm going to take my c prime, which is at 3, 2. And I'm going to multiply them all by 2 and give me a double prime. Actually, before I do the a double prime, let me show my work. We're going to do the rule, which is 2x, 2y. So it's 2 times 1, 2 times 2, 2 times 3, 2 times 3, and 2 times 3, 2 times 2. This is going to give us a double prime, b double prime, and c. You can do that again. B double prime and c double prime, and 2 times 1, 2 times 2. 2 times 3, 2 times 3, and 2 times 3, 2 times 2. So if I go over 2, up 4, there's my a double prime. If I go over 6, up 6, there's my b double prime. And if I go over 6, up 4, there is my c double prime. And then I draw straight lines to all those points. And there is our translation, followed by a dilation about the origin. Now, I wanted to point something out I did in class. When you dilate, I'm going to go from the origin and I'm going to go up through, and notice that a prime and a are on the same line. So whenever you dilate through from the origin, any point, its image is going to be on that same line. So I can draw a straight line through the origin up through all 3 of these pre-image points and image points, and they all land on the same line. Okay, so that's just a fun fact. All right, so there's the answer to this. It says graph the vertices of that and its image after the similarity transformation, and we did the dilation, or the transformation followed by a dilation of scale factor of 2, which is an enlargement because 2 is greater than 1. Now you should be able to do numbers 3, 4, and 6. Okay, now example 2 says describing the similarity transformation. So now they're giving us the image and pre-image. And they want us to describe the transformation that maps the big blue trapezoid to the little green trapezoid. So be careful what direction you're going. The blue one is the pre-image, the green one is the image. And how do we get that over there? We can't do it in one step, because if it's just dilated, it'd be over here in the same quadrant, shrunk down with this angle going in the same direction, this line decreasing as we go to the right, or a negative slope on QR. And here, this has a positive slope, so it's reflected. That's the first thing I know. So the first thing I'm going to do is look at reflecting across the y-axis. Since this is right on the y-axis here, we don't want to move r. So reflecting r is going to share the same point as r prime. S is 1, 2, 3, 4, 5, 6 away. So I'm going to go 1, 2, 3, 4, 5, 6 to the other side, and that is S prime. Q is 1, 2, 3. 1, 2, 3 would be Q prime. And P is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here is P prime. So now if I draw that, it is going to look like so. Okay, so that's the first thing. Move that in a little. Okay, so there is our image, P prime, Q prime, R prime, S prime. So that is a reflection about, oops, not very neat writing. The reflection about the y-axis. Okay, that's the first transformation, a reflection about the y-axis, reflecting across y-axis. All right, and now I see that the black trapezoid is bigger than the green one. So I know my, let's do it in red. I know my scale factor is going to be between, my scale factor is going to be between 0 and 1, because it's a shrink. So my scale factor is going to be a fraction between 0 and 1. So what I need to do is look at this and see YZ is an image of the side R prime S prime, and this is length 6. And this is length 2. So if you put the rule says if you take RS prime, you're going to put the smaller one, your image is the denominator. So RS prime is your denominator, the pre-image is your denominator. Where it goes to is your numerator. So it's YZ. So R prime S prime became YZ, and RS is 6. R prime S prime is 6, and YZ is 2. So 2 over 6 reduces to 1 over 3. And 1/3 is less than 1 and greater than 0. So my K equals 1/3, my scale factor, in other words. So now if I take the point, say S prime is at the point 6 comma -3, and I multiply that by 1/3, 1/3 times 6 comma 1/3 times -3, then I'm going to get 1/3 times 6 is 2, and 1/3 times a -3 is -1. And if I go over 2 down 1, S prime became Z. So that is true. So number 2 is a dilation, okay, of scale factor 1/3, and that's about the origin. Okay, we're getting closer to the origin. All right, how do we know it's getting closer to the origin? Again, you can do a quick assessment of that by doing this and drawing lines from the origin through the bigger vertice and see that the other one is on there. So at the point, the vertice X is on the same line, the purple line, as Q prime. Draw a line from here to P prime, and W is on it. Draw a line to S prime from the origin, Z is on it. Draw a line straight down to R prime, and Y is on that line. And that's how you determine where the point of dilation is, by drawing lines through all of the image, pre-image vertices and seeing where those two lines intersect, those four lines in this case intersect. And that's at 0, 0. Okay, so now you should be able to do problems numbers 7, 8, and 10. Okay, so example 3 is a proof. It says proving figures are similar. To prove that two figures are similar, you must prove that a similarity transformation maps one of the figures onto the other. So in order to prove that these two squares are similar, I have to prove that square ABCD, which is here, which has side lengths R, is similar to the square EFGH, side lengths S. Okay, so how do we prove that? Well, if two shapes are similar, their angles are congruent, and their side lengths are proportional. And so we have to find a scale factor and determine that they are. So I'm going to just bring in the solution from the book, but explain it as I go. So it says, prove that the squares are similar. We're given square ABC had side lengths R and square EFGH has side lengths S. And we're told side AD is parallel to side EH. Okay. Hmm. That right there is making me pause because they're not parallel. They're in line. So if I extended a line, let me show you. If I drew a line, continued it, starting, I don't know, right about here and going through, AD and EH are on that same line. These two they coincide. They're not parallel. So I've already got a problem with this problem. AB is parallel to EF. I do not agree that AD is parallel to EH unless they are saying that this square is somewhere up here somewhere. But regardless of that, let's continue anyway. And the first thing I would need to do is draw a transformation vector. So let's use red. So I want to move, whoops, transformation vector, hang on, right here. And I want it thin, and let's make it red. So I want to move A to E. So there's my direction and the distance I want to move that. So if I do that, I'm going to move this square to here. Okay. And that's basically what we're trying to do, is get A to E. Therefore, D ends up here, B would end up here, and C would end up here. So let me just bring that in with that all labeled up. Okay, so here is, let me go through the names of all these things. B now moved to here, so this is B prime right here. C moved to here, that's C prime. A became E, and D became D prime. So A is A prime here, but A prime is where E is, so we'll just call A E now. So with that said, it says the translations preserve length and angle measure. Okay, translations preserve length and angle measure. So AD is the same length as ED prime. AB is the same length as EB prime. DC is the same length as D prime C prime, and BC is the same length as B prime C prime, which is what that says right here. Okay, side lengths R, so this is R. Because all interior angles of a square are right angles, angle B prime E D prime is congruent to angle F E H. So basically what they're saying is this is a square. So B prime ED is congruent to angle FEH. They're in the same locations. They're both 90 degrees. So we just proved that this angle did not change when we brought it to this angle. When ED prime coincides with EH prime, or EH, I mean, then EB prime coincides with EF. So EB prime lies on EF. So EB prime is on this side EF. So it says next dilate square EB prime C prime D. That's this smaller square here, using the center of dilation E. So here's my center of dilation. Now remember, when I do a center of dilation, I can draw a segment from the center of dilation up through a point, and its image point is going to be on the same line as the pre-image point was. So there it is. And if I do that again, okay, and let's try that again. Make it blue, and I'm going to draw from E to G through G, and notice C prime is on that. And one more time over here, H is here, D prime is on H. So they're basically saying with the center E, I can dilate A, B prime, C prime, D prime up and make it become S. So it says, choose the scale factor to be the ratio of the side lengths of the big square and the little square, which is side S divided by R. All right, so that's where we're at now. And then when we continue, it says this dilation maps E D prime to EH. Okay, so now we're going to enlarge it to get this corner here. EB prime gets enlarged to length EF. And because the images ED prime and EB prime have side lengths S over R times R, which is S, and the segment ED prime right here and EB prime lie on the same lines passing through the center of dilation. So the dilation maps B prime to F and D prime to H. Okay, so we're just following the lines of dilation. All right, so the image of C prime lies S over R times R equals S units to the right of the image B prime. So it's this distance to the right of B prime, and S over R times S units above D prime. So it's just saying that it's the same distance. And then we're going to move it at that scale factor distance on the line that goes through the origin again. So the image C prime becomes G. All righty. So I can now conclude that a similarity transformation maps triangle ABCD to square EFGH. So square ABCD is similar to square EFGH. 90-degree angles were preserved. Side lengths were scaled in the same ratio, giving us a scale factor. Okay. Okay, so that brings us to the end of exercise 4.6 or chapter 4.6. Here are the exercise problems I would like you to try. 23 through 26 are review. We can't forget the old stuff. Okay, have a great day and thanks for watching.